All right. So we really have a couple of objectives today that we need to get done, and it's probably totally review for you, and I think you'll find it very, very easy. Well, let's get some terminology down here.
Are these matrices?
These are matrices. So we're going to talk about, first of all, what a matrix is, and then we're going to talk about doing some stuff with them. So, anybody want to, these are three examples of matrices. Anybody want to hazard a guess what a kind of reasonable definition of a matrix would be? Any ideas? Okay, well, a matrix is a rectangular array of numbers arranged in rows and columns. Okay, so does that make sense? So looking at the examples that I put up there, a rectangular array of numbers arranged in rows and columns. The dimensions of the matrix, which is sometimes also referred to as the order of the matrix, are simply the rows by columns. And when we say this, we literally say rows by columns. So even though I will write the dimensions like this, I don't say 2 times 3, I say 2 by 3. Just like you give the dimensions of a room. It's a 10 by 12 room. So what are the dimensions of this guy?
2 by 2.
2 by 2. And remember, it's always rows by columns. And actually, some kid earlier this year said, you know, Mrs. Ford, I remember that because the rows of a bleacher and the columns of a building. So rows, columns. So the dimensions of this guy, 2 by 3. 2 rows, 3 columns. The numbers inside the matrix are called entries or elements. So these are the entries of this matrix, and these are the entries of this matrix, and these are the entries of this matrix. Now, when we talk about the entries, there's a special notation that we use. So, for example, if I want to talk about this 3 right here, if that's the entry I want to talk about, I would denote it like this. I would use a small a. Any idea why I'm using a small a? Because it is in matrix A, so it refers me to matrix A, and I would say 1, 3, A sub 1, 3, that's a little subscript. What do you think? That's the number I'm talking about. What do you think the 1 and the 3 stand for? First row, third column. So if I wanted to talk about this guy right here, it would be C, little c, 2, 1. We use capital letters for the matrices themselves, and then the small letter indicates the entry within that matrix. Okay? If you happen to have, and we won't experience this, but you could in a practical application, if you happen to have a gigantic matrix with a ton of rows and columns, you would have to use a, let's say it was matrix W, you would have to use commas. If you have too many numbers, if you have more than 2 numbers, you have to put a comma in there. So that would be the 20th row, 13th column of that matrix. Okay? Now, matrix operate, one more definition. This matrix is special because it has the same number of rows as columns. It is referred to as a square matrix. Square matrices have things about them, things you can do to them that you can't do with other matrices. And we're going to talk about a couple of those things, one for sure today, maybe both of them, but in the next couple days we're going to talk about things we can do with square matrices that you can't do with other matrices. So if a matrix has the same number of rows and columns, it is square. Okay, now, what are the operations we can do with matrices? Well, we can add them, but the rules for addition are very, very strict. For example, I can't add A and B. A and B is not possible. Any idea why I couldn't add A and B together? They're not the same size. They do not have the same dimensions. You are exactly right. In order to add matrices, they have to have the same dimensions. So, could I add A and C? Yes. And if I were to add A and C, what would I come up with? Well, I mean, even if you can't remember doing this last year, you can, I bet, take a good guess. If I'm going to add A and C together, what's the answer going to be? 6, 1, 5, 4, 6. There you go. How hard is that? It isn't, right? That's easy. Subtraction works exactly the same way. Instead of adding them, you would subtract them. Exactly. What's the rule? They have to have the same dimension. So I promise you that on a quiz or test, there's going to be a question that says this, and you're simply going to say, can't do, not possible. There are many matrix things that aren't possible. The rules are very strict. So it's not uncommon to say, I just can't do that. All right, what do you think this means?
Double C.
It means take 2 times all the elements in C. And guess what we refer to the number 2 as? Well, it truly is a coefficient, but think back to vector land. What did we call that in vector land? We called it a scalar. The language of vectors and matrices is the same. Many of the operations are the same. So we will talk about this as scalar multiplication. And it is exactly as you guessed. Scalar multiplication, times this by 2 would be that. I mean, it is that easy. Now, what gets a little bit more complicated, more complicated, not hard, but more complicated, is matrix multiplication. This is scalar multiplication. We're multiplying by scalar, and that's a breeze. But what if we wanted to multiply A times B? This is matrix multiplication now. All right, well, what are the rules for that? Well, they're different than for addition and subtraction. What are the rules for addition and subtraction? They got to be the same size. Okay? That is not the case with matrix multiplication. With matrix multiplication, you look at the dimensions of each matrix. Okay, so what did we say the dimensions of this guy are? 2 by 3. What are the dimensions of this guy? 2 by 2. These cannot be multiplied. And the reason they can't be multiplied is because in order to multiply, these have to match. The row, or the columns of the first have to match the rows of the second. If they don't, you can't do it. Okay? So, let's do a problem we can do. What if I turn that around and made it B times A? Now, would I be able to multiply? Will this work? Well, what are our dimensions here? 2 by 2. What are our dimensions here? 2 by 3. What's the rule? These got to They do. So now I can multiply. Now before I actually do it, I want you to make an observation. With regular numbers, like 6 times 8, does it matter if I do 6 times 8 or 8 times 6? No, we call that commutativity. Regular multiplication is commutative. Is matrix multiplication commutative?
Yes.
No! Look, in this order, you can't even do it, right? So it does make a difference what order you multiply in when you are multiplying matrices. Okay. All right, so we figured out now, you know our rule, this can be done. The answer will be a 2 by 3. So when I multiply, these two have to match, and then these guys tell me how big my answer is going to be. So my answer is going to have 2 rows and 3 columns. So if I were multiplying a 3 by 5 and a 5 by 8, I can do it,
3 by 8.
and my answer would be a 3 by 8. That's how it works, okay? Now, our job is to come up with the 6 numbers that represent the product of these two matrices. Now, remember when we wrote our dimensions? That was always, the first number is always the row number, right? So we always do rows first. So I want you to draw a circle around this row and a circle around this column. Now, do you notice how they have the same, there are 2 numbers here and there's 2 numbers here, right? Now I want you to take the first number times the first number and the second number times the second number, and I want you to add them together. So I'm going to take 1 times 1 and 2 times 4, and I'm going to add them together. I get 9. That's what goes right here. Now notice, this number is in the first row, first column. So how did I get it? I multiplied the first row times the first column. So when I move over to this spot, I'm going to take the first row times the second column, because that's the first row, second column. So I'm going to take 1 times 2, 2 times 5, and add them together. So that would be 12. Now kids, you are doing an operation that you've already done a few weeks ago. You may have forgotten it already. I hope not, because we have an exam coming up. But when we had vectors, if we had a vector that was 1, 2, and we had another vector that was 1, 4, and I said find the dot product of those 2 vectors, v dot u, how did we do a dot product? We took x times x, y times y, and added them together. So what are we doing here? We're doing 6 dot products. We're taking first times first, second times second, and adding them up. So here we go, fill in the rest. See if you can get the rest of that filled in. Keeping in mind that whatever number you're looking for, that's the row and the column that you multiply together. Anybody have any problems with making mistakes? Are we good on that? Everybody match okay on that? All right, let's try one more. Let's multiply b times c. thing you gotta do? Before you jump in and start messing around with it, what's the first thing you wanna check? Can I even do it? Because a lot of times you can't even do it. Can I do it? Well, what are my dimensions here? 2 by 2. What are my dimensions here? Oh, great news. It's gonna work, right? And it will be a 2 by 3 matrix. All right. So go ahead. I'll just shut up, but if you have a question about a particular number, we can talk about it. It's easy to make mistakes here, so.
Do you ever divide matrices?
You do not divide them, but you can multiply by their inverse. So we'll talk about that tomorrow. Maybe today, but probably tomorrow. We still have a couple more things to talk about today.
This form. What are matrices used for?
Oh my goodness gracious. Matrices, when you have volumes of data, like if you take a business calculus class where you are analyzing volumes of data, the data is often put into a matrix. So for example, the column or the rows of the matrix might represent the months. So you might have a January, February, March row. And then these might represent, this might be your expenses that month. This might be your inventory, you know, and the next column might be something else. So when you have lots of pieces of data representing different things, you can put it in a matrix because each row can represent something and each column can represent something. So that if this was January, February, and this was expenses and profit or whatever I said, I can't remember, this number would represent the expenses in January. And this number would represent the profit in February, or, you know, whatever the columns and rows represented. When I was doing my graduate work, getting my master's degree, it was so interesting because, remember, I have English and math both. So in one session, I'm taking some Shakespeare thing that's like mind-boggling, and then I'm doing what's called a projective geometry class, and my project was to manage a buffalo herd in Wyoming. I mean, that was my job. So I had a huge matrix. I mean, it was gigantic because I had to know fertility of the females, fertility of the males, how many males it took to, you know, for the herd to propagate. What's the, how many babies survive when they're born? I mean, how many times they have twins? I mean, all this data that had to be managed, and I did it all through matrices. It was an immense project. Oh, you absolutely can, and we're going to do that in a little bit. Not right now. Now, you are required to be able to do everything we've done so far by hand. But certainly, if I'm multiplying an 8 by 12 times a 12 by 7, I do not want to do that by hand. So we're going to talk about how to do the calculator, and we're going to do, I think it's Friday, everything we do is going to be on the calculator. But these things you need to know how to do by hand. But will your calculator do it? Absolutely. For these small matrices, it really takes longer to get it all in than it does just to do it by hand. But we're going to talk about how to do it. All right, so everybody good with these numbers? Okay, so here's the next thing we're going to talk about. If matrices are equal, if somebody says to you, matrix A equals matrix B, and the best thing I can do is have you look in your book. Let me find the page number. Would you look on page 591 of your textbook? And for those of you without a book, shame on you, as usual. But this is problem number 32. This is just an example of matrices that are equal. And it's a pretty simple example. But here's the point. If the two matrices are equal, then that implies two things. First of all, they have to be the same size. Clearly they are. This is a 2 by 2, this is a 2 by 2. They do not have to be square, but they have to be the same size. They have to have the same dimension. Then, if they're equal, the entry in the 1, 1 spot here has to match the entry in the 1, 1 spot there. Does that make sense to you? So in this case, the directions say find A and B. Kids, it's easy. A plus 3 has to be 4, so A has to be 1. And 5 has to equal B minus 1, so B must be 6. So when you're told that matrices are equal, it simply means that they're the same size and their corresponding entries are the same. Easy, right? Makes sense. Okay. Now, I told you a little bit ago that there is something special, or actually there are lots of special things, about square matrices. One of the special things that we can do with square matrices is find what's called its determinant. Now, please don't get this word confused with discriminant. Who remembers what the discriminant is?
Not bring it up.
What?
I said if you don't bring it up, don't get them confused.
No, we have to know what the discriminant is. What's the discriminant? B squared minus 4AC. It's the part of the quadratic formula under the radical. That's called the discriminant. We're talking about finding the determinant. Now, I'm not going to give you a definition of the determinant. The determinant is just a number associated with every square matrix. Every square matrix has a determinant, and the determinant is just a number. The definition is actually how you find it, so I'm just going to show you how to find it. If the matrix, we'll just start with this one, if that's my matrix, then the determinant of the matrix is denoted with vertical bars. Okay, vertical bars. That stands for determinant. And it's calculated like this. So the answer would be -2. Now, can you tell what I did? What did I do there? How did I get that number? I took 1 times 4, and I took 3 times 2, and I subtracted them. And that's how you find the determinant of a 2 by 2 matrix. So if you had to evaluate this determinant, that determinant, what would you tell me the answer was?
You across 15 minus 0.
It would be 3 times 5 minus -1 times 0. 15. Remember, when you times by 0, it's a 0, right? All right, so we'll do one more. What would that one be, the value of that determinant? It would be 12 minus -5, or 17. So if you walked in here tomorrow and I said, take out a half sheet of paper, evaluate this determinant, everybody'd be able to do it, right?
Yeah.
Okay, now remember, only square matrices have determinants. So we've just gone through some examples of 2 by 2s. So what's the next logical step? 3 by 3s. We're not jumping to 4 by 4s. We're going to 3 by 3s now. So let's look at a 3 by 3. determinant. All right, we're going to evaluate this guy. Now the procedure is actually exactly the same. It's just on a bigger scale because there's more numbers to deal with. So here's what I want you to do. I want you to take these first two columns of numbers, and I want you to write them down right next to the determinant. Okay, so I took this column and this column, and I wrote them down right here. Now, just to remind you, when I had a 2 by 2, what multiplication did I start with? Right here, right? And I always tell kids, and for some reason we mess this up, I always tell kids, when you wrote that set of numbers, what was the first number you wrote down? 1. Where do you start multiplying? With the 1. So I'm going to come over here and I am going to multiply these 3 numbers together. Now I have 3 numbers, but I'm going to multiply them all together. So that's going to give me a -1. But this is bigger. So now I not only have to multiply that string, I got to multiply this string. And that gives me a 20. And then I got to multiply this string. So in other words, I got to work all the way across, hitting all of those diagonals. So that one gives me a 0. Now I'm going to total those up. So I'm going to get a total diagonal in this direction of 19. Now when I did a 2 by 2, I only had one set of numbers. That diagonal was 4. Now I have all of this, so I get a total diagonal of 19. Now guess what I'm going to do? Here, I would do this one, right? I'm going to do the same thing over here. I'm going to start right here, and I'm going to multiply those together, and I'm going to get -15. And then I'm going to multiply these together and get 0. And then these 0. And then I'm going to total those up and get -15. Now remember, when you did a 2 by 2, this diagonal gave you 4, this diagonal gave you 6. What did you do to those 2 diagonals? You subtracted them. So now I'm going to take my 19 and I'm going to subtract the -15, and my answer is going to be 34. So the process is exactly the same. Take these minus these. Okay? So let's try another one. Okay, so here we go. Again, your calculator will do this. And we're going to use the calculator for anything bigger than a 3 by 3. But you need to be able to do a 3 by 3 by hand. All right? So what do we do? How do we get this ball rolling? We take the first 2 columns and we very carefully copy them. Which 2 columns do we copy? The first 2. All right, here we go. Start right here. That diagonal gives me a 10 and a 0 and a -9. Everybody okay with that? Here we go. Got a 0 and a 0 and a -4. So what's my answer? 5. 1, 1 minus negative 4. Everybody okay with that? All right. Now, the question you are probably asking yourselves right now is, okay, Mrs. Ford, this is really awesome. I'm going to get quiz points for this because this is easy and I'll get it all right. But what do we have determinants for? Why do we even have determinants? Well, I'd like to give you, the study of matrices is called linear algebra. And when I was in college, undergraduate, I took a whole class in linear algebra. I mean, there's a ton of stuff you can learn. And a whole chapter is devoted to determinants. There's so much you can do with determinants. Here is an example that's applicable to us right now. In last night's homework, you were solving equations, or systems of equations like this, right? And what tools did you have at your disposal? Elimination, substitution. You could graph it on, if you had a calculator, you could graph it on your calculator and do that. Well, there's another method that when I first go through it, you're going to say, I would never do that in a million years. But if you think about it for a minute, it actually really is a very efficient way of doing the problem. It's a method of solution called Cramer's rule. Did you do this before? So you remember how slick this can be. When we do Cramer's rule, we are going to set up, we're going to solve for x and y, and x and y will both be fractions. Now, they may ultimately turn out not to be fractions. For example, we may get, 8/4, which would reduce to 2. But the structure is always going to have them set up as fractions. The denominator of both fractions will be the determinant of the coefficients. Remember how that works? So I take my coefficients right off my variables. I'm going to evaluate that determinant, and that's going to be the denominator of both my x and my y. So, what is the value of this determinant? -5. So I put a -5 here and a -5 here. Now, if by chance that determinant turns out to be 0, we have a problem, don't we? What's the problem? Can't have a 0 in the bottom. So what does that tell me? Well, it tells me that my system is either parallel lines or the same line. Does that happen sometimes when we do substitution and elimination?
Mm-hmm.
Yeah. With Cramer's rule, you know right away, because if that determinant turns out to be 0, you know you don't have a unique solution. They don't do this. All right, the numerators. The numerators are other determinants. To get the x numerator, take these two numbers, the constants, the 4 and the 1, and paste them in on top of the x coefficients. These were the x coefficients out of the equation, right? If you are solving for x, cut these out and paste them here. So that determinant would look like 4, 1, 1, -3. If I am solving for x, I take my constants, I cut them out, and I paste them right on top of my x coefficients. So I have 4, 1, 1, -3.
The same thing.
When I solve for y, I do exactly the same thing, only I paste those on top of the y. So that would look like this. So you can't be confused. If you're solving for x, you replace the x's. If you're solving for y, you replace the y's. And then you evaluate those. So let's see, what would that one be? What would that numerator be? Negative 13 over negative 5, so that's 13/5. And this one would be negative 7 over negative 5, so that would be 7/5. So these two lines intersect at the point 13/5, 7/5. Now, in the real world, who cares how you solve the system? I mean, you have all these tools, substitution, elimination, Cramer's rule, whatever. Do whatever you want in the real world. But I want to emphasize the benefit of doing Cramer's rule. I have students who do Cramer's rule all the time. Because what does it eliminate the need for you to do? Deal with the fractions. Remember, if you do elimination, let's say, that's my personal favorite, if you do elimination and you solve for x and you get 13/5, that's great. Now what do? You plug it in. Now, we're grown-ups, we can deal with that, but it does mean dealing with fractions, right? If you do Cramer's rule, do you actually deal with any fractions? You got fractional answers, but do you have to do any fraction arithmetic? No. So if you are one of those people who has issues with fractions, which frankly some of you are, on the last test we had a problem. It was like 4/7 plus 1/3. I'm making that up, I don't remember the fractions. Somebody said the answer, that was 4/7. Somebody said the answer was 5/10 or 1/2. This is a problem, right? If you're dealing with fractions, you need common denominators and all that kind of stuff. This is not right. Speaking of another thing that I can't believe, we had a quiz, on yesterday's quiz, had a cry, I don't know, I was making up something. And I had a bunch of people in this class do this. I just wrote on your paper. What does the order of operations tell us? We multiply first. You don't be adding these two together, people. Under any circumstance, you would not do that if they're not in parentheses. I think there were 6 of you that did that. I mean, it was amazing. Okay, well, that's neither here nor there. Let's try another Cramer's rule problem. Make sure you got it under control, and then we'll move to the next step. All right, here we go. Let's run through Cramer's rule one more time in case we have a quiz tomorrow. All right, here we go. Here we go. How's it work? Well, what's the first thing we need to figure out? The denominator. Now, somebody asked me the other day, Mrs. Ford, does it really matter what we do first? And the answer is, I guess not. But the nice thing about doing the denominator first is if it turns out to be 0, you're done. Right? So that's why I like to do that first, on the off chance it might be 0. So there's my denominator. It is not going to be 0. What is my denominator going to be? Negative 14. So x is going to be something over negative 14, and y is going to be something over negative 14. We can do that in our head, right? That's easy. Now, what's our numerator? Well, for x, we're going to take out the 3, or we're going to take the 3 and the negative 7 and paste them right here, right? Because these are the x numbers. So we have 3 negative 7, 1 negative 5, and then we'll do the same thing for y, only we'll put the 3 and the negative 7 here. Everybody okay with that? All right, let's evaluate them. So what do we get up there on top? Please watch your SIGNs. That's going to be -15 minus -7. So that's going to end up being -8, right? Over -14, which is 4/7. So my x is going to be 4/7. Here I've got -14 minus 12, which is going to be -26 over -14, or 13/7. Now, I don't know about you, but that arithmetic is easy. Much easier than doing elimination or substitution would have been, I think, personally. I think. You all right with that? Is your hand up, Zach?
Yeah. So if we're doing Cramer's rule and we get a 0 and we're just like done, how do we know if it's the same equation or it's parallel?
Well,
Or does it really matter?
Oh no, it matters, and that's when you just have to like pay attention to what's going on. So for example, this would be a situation where your determinant would be 0. So I get 2, 1, 4, 2. That determinant is going to be 0. Do you see that? So I know immediately, okay, I've either got the same line or I've got parallel lines. So you've got a couple of choices. Here I can tell that if I took this equation times 2, I would get this one exactly. So these are the same line. These are the same equation. If you can't tell that, then you could always, like, put this in slope-intercept form, put this one in slope-intercept form, and either they're going to be exactly the same, or you're going to have a situation where one says this and one says this, which means these are parallel lines because they have the same slope, but they have different intercepts. So you can usually just look at them and tell that they're multiples of each other, but if the numbers are weird and you can't quite tell, then you can put them in slope-intercept form and see if they match or not.
Okay.
If they match perfectly, they're the same line. If they'll always have the same slope because they'll either be parallel or the same. If these match, then you know they're the same line. If not, they're parallel to each other.
Okay, awesome. Thank you.
Okay? All right. I don't have time to start the next thing. We'll be right in the middle of it when the bell will ring. So I'm going to stop right now. Your assignment's in Schoology, so you can take care of that.